Hello there. So let's talk about the role of glycolysis in cancer. This is quite important, actually. And it goes back, I've already mentioned that some glycolytic enzymes, let's say pyruvate kinase, are mutated and predisposed in cancer. But the relationship between glycolysis and cancer goes way back and does have extremely important diagnostic applications today, okay, which we will describe. So Otto Warburg in the 1920s, so about 100 years ago, noticed that the rate of glycolysis in cancer cells is very high. So cancer cells prefer to do glycolysis as opposed to, and fermentation as opposed to oxidative phosphorylation. So they do the sequence of events that we described that are, let's say, characteristic of yeast. So in some way they act like yeast. They just consume a lot of glucose, they get their ATP out, and they spit out also lactate. Okay, why is that? The idea is that they get enough ATP to cover their energy needs, but if you're a cancer cell, you won't divide. So to divide, you need biosynthesis and you need building blocks. And this is where glycolysis becomes important. It's not a matter of energy efficiency here. It's a matter of getting enough raw materials to make a new cell. So the requirements are kind of like yeast here. I mean, the context. That all it cares is just to divide, and it takes glucose, it does its glycolysis and fermentation, it gets its two ATPs that it needs, and at the same time, because it makes more yeast cells, or in this case, more cancer cells, it has enough building blocks to make new cells, to do biosynthesis. So it is not a universal phenomenon of all cancers, but the majority of them actually behave exactly as Warburg had described. So about 2/3, maybe slightly more, do glycolysis and fermentation as opposed to oxidative phosphorylation. Now that has important implications. So that's a property of not exclusively of cancer cells, but of most cancers. So it has been used in diagnostics. I mean, how are you going to find these cancer cells? You can use that as a signature. So you use glycolysis as a signature of cancer cells, and you can pinpoint where the cancer cells are. So I'm sure you've heard about PET scans, and that's really what it is. What happens in this case, you are giving an isotope. The patient is taking an isotope, which is glucose, really, except that this hydroxy carbon, the hydroxy group next to the aldose, to the carbonyl, sorry. So to the terminal carbonyl in glucose, so glucose is an aldose. So the next one is going to normally is a hydroxyl carbon, so it's another oxygen. But this analog has a fluoride on it, 18 fluoride. And the reason why that happens is it is not going to be able to be metabolized in glycolysis. It will be taken up, okay? It will enter the cell just like glucose does with a passive diffusion, facilitated diffusion, passive transport mechanism. Hexokinase will phosphorylate it at the 6th position right here, okay? And then, however, the next step cannot utilize, which is phosphoglucose isomerase to get to become fructose, okay? At this point, what's the next reaction? The carbonyl will move to this position, but it cannot move. You cannot isomerize glucose to fructose because now you've stuck a fluoride right there, right? So what you will measure is uptake of fluorodeoxyglucose by cells, including cancer cells that do a lot of glycolysis. It's going to go through the first step, and then it's a block. And then all you have to do is find out where the fluorodeoxyglucose, the 18 fluoride fluorodeoxyglucose, ended up in the tissues and organs of the patient. Just to remind you again, phosphoglucose isomerase was reaction 2 in glycolysis, and you really want to make this hydroxycarbon to carbonyl and this carbonyl carbon to hydroxycarbon, but of course here you have the fluoride, so it won't happen. Okay? So the reaction cannot proceed. All right, so then you look at where the isotope ended up, and you find some tissues that are normal. You can see it here, but that's the brain that uses a lot of glucose, so that will light up. So everything that lights up, for the most part, is a cancer cell, except the normally high glucose consumers which are the brain. There is some in the kidneys, which I believe you see here, and some in the down the urinary tract. But the rest, big blobs here, which I believe they're, let me see, they're upper right side quadrant or left side. I can see, but that's probably the liver right there, and it highlights all the liver tumors in the patient. So this is what physicians do, oncologists, when they prescribe a PET scan, and you will go have the PET scan, and this is the image you get. Okay, because again, unfortunately, this tumor is it loves glucose. It will pick it up and do glycolysis and the fermentation and grow and grow and grow and divide and generate more cancer cells. All right, so we'll close at this point, and we're going to finish with the next video, which is actually my favorite part of this whole series of glycolysis videos. It has to do with the evolution of glycolysis and why glycolysis is the way it is. But for that, you have to wait for the next one.